Hello, everyone. Welcome to PyData Global 2024. My name is Arlis, and I'm the developer advocate at NumFOCUS. And I am very happy to introduce you to Leonie, who is going to give a talk named Using AI to Spot Deforestation-related Cows on Satellite Images. I'm interested. And Leonie is a land system scientist and postdoctoral researcher at the Global Land Use and Environment Lab at the University of Madison, Wisconsin. So, Leonie, take it away.
Hey, everyone. Thank you for this kind introduction. I'm Leonie. And yeah, thank you all for joining today. For some of you, it might be already quite late. For us in Wisconsin, it's only afternoon, but still, yeah, winter was also like hitting hard here. So I'm a little bit with a cold, but yeah. So keep up the mood, I hope, for this talk. So yeah, as we were saying, I'm a postdoc at the Nelson Institute in Wisconsin, in Madison. And this is going to be a very applied talk. I'm a land system scientist, so I use a lot of Python coding and these models, but still, I will tell you like what motivates me in my work mostly. So this is the Amazon biome, or like the conservation of tropical forests in general. During my work, I was able to visit this place several times. It's a very special place on our planet since it's the forest with the highest biodiversity. It has amazing fruits and nuts there that are like endogenous to the region, and also many commodities that we use on a daily basis are from that region, like cacao and rubber. So yeah, this place is important, obviously, also as a carbon sink. So when we look at climate change, it's a regulator for the climate of the whole continent. And then its preservation is not only important for the environment, but also like for the people that live there. If we think about that, indigenous people have been living in this forest for over 12,000 years, and their livelihoods depend on it. And now there are over 20 million people live there. Relying on that ecosystem. We all know probably that this forest is fragile. So there was a lot of deforestation going on in the past decades, and now over a fifth of the forest is cleared. And not only that, there's also a lot of fires and forest degradation going on. And these three factors perpetuate each other such that it's very difficult to get a hold on it. So for this talk, we're going to focus on cattle ranching in the Brazilian Amazon, while 60% of the Amazon lies within the Brazilian borders. And also they're like the biggest deforestation hotspots. And then most of the areas that are cleared where the forest is gone, you will find pasture afterwards, and this is linked to cattle ranching. So 90% of all the deforested land has been pasture at one point. This is linked to the livestock sector in Brazil. Livestock sector is a really important sector for the Brazilian economy, and this is why we're also like always have an eye on like the production system of in this sector. So it's in the Amazon, stocking rates have been historically low. That means the animals per hectare is a very low number. And if you think that there could be like an improvement in productivity, that means that we have more animals per area. If we think about some really like regulations that we have to have in place, for example, it has to be like done in a sustainable way. It has to comply with like animal health restrictions, and then we have to make sure that after we intensify production, we do not expand more into the forest. But in principle, this idea of trying to increase stocking rates, like having higher production on less area, could be like a way to make more space for the forest to regrow, or at least to be preserved. So, but before I continue, I want to present you my collaborators. So this work and all the cattle counting work has started as my PhD at the ETH Zurich with Rachel Garrett and Jan Wegner, and with my local collaborators in Brazil, in Embrapa and Acre. And now I'm working with Holly Gibbs at the National Institute in Madison, Wisconsin, with several people, Kaina, Rains, Leah, Utai, and Julia, and Eileen, who have been helping me to improve my AI model. So before I go into how I count cattle from satellite imagery, I want to give you a little overview of the history of animal counting. So this all started 15 years ago with Landsat satellites. That's like a 30-meter resolution satellite that has been going on for decades already. And they started to see this penguin feces in the Arctic. And we're like, okay, that means that there are some penguins there. And then a couple of years later, these very high resolution satellite images came along with way better resolutions, 0.6 meter resolutions, and people started to see actual individual animals on those images, like your individual seals. And it's not a coincidence that both of these examples are in the Arctic. That makes sense, right? Because that's where we have the highest contrasts of background and animals, so it's quite easy to spot. So there was this major advancement of getting better resolution for satellite images. And then the second big advancement related to that task was obviously AI. So yeah, in the past few years, there were several studies that used different convolutional neural networks to spot animals and count them. So here's just two examples. They used the object detection, faster RCNN to detect elephants, or UNet, which is more like a segmentation model to detect these albatrosses from birds and special bird islands. So yeah, some time ago, before I even started my PhD, I was just scrolling through Google Maps and I zoomed into the Amazon forest. And I saw that these individual cattle are actually visible on the images. And then I was like, oh, it would be very cool to develop a model, an AI model that could detect and count these cows. And then I quickly learned that I need very high resolution images. That's around 30 centimeter resolution satellite images to be able to see those cattle. From a computer vision challenge, you can think about two different, from a computer vision perspective, we can think about two challenges. So one is, yeah, these animals are very small. They're often appear in herds, so maybe they crowd around some water or somewhere else. So they cluster together. And then the image background can be very diverse as well. So it very much depends, and we will see that later in the talk, whether there's clean pasture or a lot of regrowing vegetation or just burnt areas and so on. So those are the difficult tasks when it comes to counting. Because of that occlusion and clustering, I chose to use a congested scene recognition model that is a density-based convolutional neural network. And basically what it does, it works with this concept called dilation. So that's the kernels of the CNN are kind of spaced out with zeros in between, and that makes it the model to learn more about the context of the scene and less about the individual objects in these bounding boxes that we usually think about if we think about object detection. And this has been done before, for example, to count people in crowds. That was the first paper using congested scene recognition, and then also has used before for counting cows in the Amazon. Well, the initial task to do if we really want to develop such a model was okay, how do we even compare the cattle on these images visible to the actual cattle on the ground? So I got the data from the vaccination agency in Acre, so the animal vaccination agency, and could compare like actual cattle numbers on 21 different farms to the cattle on the images. And then I see that, okay, not all of these cows are actually visible, which makes sense if you think about it. I mean, most of these cows were probably like, not most of the cows, but some of the cows were maybe like prefer to be under a tree because it's hot in the Amazon, right? So this is definitely a challenge which it will be difficult to cope with, because yeah, what can we do about it? If they're not visible, they're not visible. But for now, we account for it with a scale factor of 1.3% on, yeah. So then the big chunk of the work was like developing a training data set to be able to train a convolutional neural network. So in a semi-automated approach, I labeled cattle and then developed these heat maps, which will be like my target for this model. Semi-automated in here means that I started to train the model, and then with the new predictions, I just corrected the new predictions and so on. So the model will like improve with my new input of the corrected predictions. I trained the model in PyTorch. Here you see the architecture of the original congested scene recognition model, with like encoder that was already trained on ImageNet, a VGG encoder, and then like the decoder exactly has that dilation rate of 2, which helps to learn the context of the scene. And then I also use an ensemble approach for modeler robustness. That means I have like 5 different models working simultaneously. And this is how it looks in the end. That's my model. That as an input, we have this image tiles of satellite imagery, which is in the RGB space. And then as an output, we have these heat maps. And if I sum up the pixel values of the heat maps, it will give me the actual number of this cattle in this image tile. And then I can do that for the entire pasture landscape in the Amazon, which will then tell me where are these cows in space, which has then various like use applications for research. Here we see that I predicted on different image patches throughout the Brazilian Amazon for the years 2018 and 19, over 500,000 of animals. And then I started to look into like where these animals are, like inside of property boundaries or outside of property boundaries. So there's a research paper about how I then derive stocking rates, and have a regression model on like how stocking rates are related to deforestation, but we will not go into that now, so you can read the paper if you want. So rather, I will talk about like what were the model limitations that I encountered after looking at all this data, and how I tried to like account for them. So one thing was that my training data set was focusing on this pasture area, so the generalizability in like for different landscapes was not working so well so far. I saw a lot of like false positives still. And then we have that problem that I talked about before, like there are some undetectable cattle. The more like trees we have on the landscape, the more they will probably hide under the trees. So there's like this problem of false positives, and I will tell you now why this is the case. So some areas will look like this, and then it might even get difficult for us as a human with the like human eyes to distinguish between cow and something else. Like especially here in the second image, you will see that sometimes like little trees would reflect the same way like maybe a white cow would do. So so you've probably seen in the images that most of these cattle in the Amazon are white. So we're dealing with white cows, and then sometimes white reflectance of other objects like trees and stones. What we then try to do is the model has to learn how to handle these heterogeneous areas. So and in addition to all the annotated images that I had before, we now started to like do this in a more thorough way and look at very different sites throughout the entire Amazon with very different backgrounds, coming up with like over 5,000 new image tiles. And then also we specifically targeted this like very heterogeneous landscapes and labeled them together with my students. So yeah, for the generalizability problem, we tried to account for that with retraining the whole model with this calibrated and heterogeneous training data. And then for the false positives, we also try to include a binary classifier of these image tiles before we use the density-based approach to filter out the most difficult images. Before we go into the results, let's make sure we understand the evaluation metrics. So there are three evaluation metrics. The mean average error, which is basically giving us the number of, I don't know, if there are 2 cows on the tile and I predict 1, then the mean average error would be 1. But it's always positive. That's the important thing. The percentage error then like accounts for like how many. So it's dependent on the actual number of cows. So it would not account the error image. The error would not be as big. Like if we have like 20 cows and the model only counts 19, then that error would be way smaller than for like lower number of cows. And then the mean error is the error that preserves the sign. So positive and negative errors will cancel each other out. So it will show us the bias of the model towards like false positives or false negatives. Here we see the model performance of the old model with the old data set as a baseline. So the mean average error is like around 0.8. And then we predict with this old model, we predict the cattle on the new data set, and we see that like all these metrics explode because the model is not prepared for accounting for all these new heterogeneous areas. So if we then like after training the new model and predicting on the new data set, we see that it now has learned to handle this heterogeneous regions. So we like lower all these errors again, and then we see that the mean error is instead of negative is positive. So it even filters out maybe a little bit too much now, but which is fine because I think it's still like in the range. So to visualize it a little bit better, I brought like just one example. So here's the ground truth, an image where the ground truth was labeled as 0 cows, so no cows at all. And you can see that they're like, all these like little white dots still that might be little trees. That's how the old model was like handling it. It would like see a lot of different cows, especially in the middle of the region. And then the new model kind of has learned to handle it. So with new training data, we were able to account for this problem. But we're not 100% like happy yet with it because there will still be some examples where it would not distinguish between heterogeneous background and cows. So we kind of like as a pre-processing step, we included a binary classifier that detects the herd, or like just has like either it's a cattle herd or it's background, and you filter out all the background tiles. And before we hand it over to the cattle counter that then counts the individual animals. And this was done by one of our students as well. So she tested a lot of different binary classifiers and thought, like in the resulted in the exception model as the best model. Here you see the class distribution. Obviously, yeah, cattle will still be very sparse in the landscape, so we had a lot of background images. And here you see the same result as before again. So the two, the new model like predicted on the old and new test set, and together like with the exception model, we even see that the errors go down a little bit more, except for the mean error, which is now, at least for the new data set, is much higher, and which makes sense because this is something we would maybe expect. We filter out right now. We filter out a little bit too many heterogeneous images, even though there might be still cattle like labeled on it. So, but having that would be like a high recall. So having a high recall for now is fine because we rather want to be conservative with our cattle estimations. So yeah, now with this new model that seems to be improved a little bit, we can think about more applications of it. Like, and one like interesting application would be to think about where in the landscape these cows are, and control, kind of try to relate it to the cattle supply chain data that we have, and which is used for a lot of different policies. So a lot of companies try to clean their supply chains with only with animals that are produced in a sustainable way without deforestation behind it. So there's a lot of work going on about trying to map supply chains and find out about the suppliers of slaughterhouses and so on, and try to map them throughout space and see if they're compliant with policies. And this method will be can be used for like a lot of verification and control mechanisms, and also for research questions will be important to see like where in space are like all this clandestine or more illegal or informal cattle produced, and how are they sourced, how they're going into the supply chains. Another very interesting application is looking at cattle in protected areas specifically. So here you see like this whole green area is a protected area in the Amazon in the state of Rondônia, called Sete de Setembro. It's an indigenous territory, and you see that like on the border, so on the blue line, there's like all these cattle that move into the territory. So if we zoom in, we can see that, and in green, you see like the property boundaries of different cattle ranching properties, how these cattle, like from the cattle ranching properties, go into the territories. And together here in Madison, we work together with different Brazilian prosecutors and also the environmental police, IBAMA, in Brazil, and they can utilize this kind of data then to enforce regulations and maybe even take action on the ground. So this is all like applications of this method. So we've seen that the cattle density estimations this is a new method that we can use for like study cattle related land use and other things, and performance was going up after we trained with this new heterogeneous data, and also the binary classifier as a pre-processing step seems to work pretty well. Also, I want to mention that this is now, we know now that if we take more training data, we can teach the model to predict cattle in different landscapes. So that also kind of implies that we were able to use it in lots of other geographies where cattle ranching also might be linked to deforestation or other kinds of environmental degradation, which can be cool, possibly. So with this, I just wanted to say again that there's a preprint online where I explain more in detail how this method works, and also have some results on stocking rates and the relation to deforestation. So if you're interested, please reach out or read the paper. And with this, I thank you very much.
Awesome. Thank you very much, Leonie. We do have a couple of questions in here. So I will start with the first one here. Thank you for this interesting topic. I agree. And presentation, couldn't the background issue be solved or reduced using the NIR band rather than just RGB?
Wait, let me just, I want to have this up. Yeah. Yes, the problem is that we only have the RGB data right now. So because that's usually like this very high resolution satellite images come with like RGB only. So yeah, but I guess in theory it would be helpful to have any other like spectral information to learn from. That would probably work. Yes. But it's not available to us right now. Yeah. Which is a problem in general. Like this very high resolution satellite imagery is pretty sparse. That's why we can like not think like in a big picture. But
great. And another question here, were the false positives mostly other animals or physical features?
I don't think that there are a lot of other animals in the Amazon. So it was really like, I mean, that sounded a bit wrong, right? Like, but in these pasture areas where people are like producing animals, like in like a animal husbandry kind of way, I think that we're talking about cattle only in the Amazon. So we would not expect any kind of other animals. But of course, there's some exceptions. But there are like stones and just bare soil that might be like have this white reflection, or little trees which might also reflect in a weird way.
Great. So that's it for questions. If there are any other questions, we've got a new one here. Any risk of double counting as the animals are on the move?
Yeah, that's a good one. Because if you think about it, like these are like the images are obviously only snapshots in time. And if you take another snapshot like 5 minutes later, it will be different. But that's like, as I said, like the images are so sparse for now that we do not have to think about that issue so much for now. So we're rather happy if we have like one image per year or something. But the temporal resolution is very interesting to think about. Like, how would you handle it if we had several images in a row? We could probably see how the animals move, which would be cool as well.
Awesome, I agree. Alrighty, are there any more questions? Something in the chat? Yes, folks. Great, you got some nice comments there in the chat, but at this point in time, I don't see any more questions. And since we are at just close to the end of this session, on behalf of all PyData Global, I'd like to say thank you very much for your presentation. And to all attendees, thank you very much for joining. As I say, many of our presentations, or most of them, will end up on our YouTube channel at some point in time. But with that, I will say thank you again, Leonie, and thank you to everyone, and we will end the session now. Take care, all.